Today I'm going to talk about signal integrity considerations for an ideal PCB stackup. Now when I think about the ideal PCB stackup, there's really three major areas that come to mind: EMI, power, and signal integrity. So let's talk about each of those. For EMI, I think the most important thing is to have a solid ground plane. So you want to have just one solid ground plane to act as your return path in order to minimize the loop area so you don't cause a lot of extra radiation. Now, one thing I see a lot of people still have questions about is whether they should actually have a split ground plane, so have a separate ground plane for digital and a separate one for analog. And you actually don't want to do that. So a better way to do that is to do what's called partitioning. So while you still have one solid ground plane, you keep your analog and your digital layout and chips and devices separate so that they really can't couple with each other. And there's lots of companies that have a lot of good app notes on that where you can learn more about that. Now the second thing to consider is power. And really when I think about power delivery network and power integrity for PCB stackup, I think I want to keep the inductance low, because a low inductance means a low impedance, and the low impedance means that your voltage ripple is going to be within your specified limit. So let's say it's a 3.3 volt interface and you want to keep the noise on it to plus or minus 5%. You want your impedance to be low, and inductance influences how high or low your impedance is. And really the key to having low impedance on your PCB stackup is all about decoupling. So it's a mixture of having your power and ground planes closer together, so you have tight coupling, so you get that interplane capacitance, and also involved with the chip and the package. Lots of times that has more than enough capacitance, so you don't even really need a lot of that interplane capacitance. And then the other part of it is actually your decoupling caps, putting them close to the power pins in your IC chips. And really, it's really important to consider the loop inductance of your decoupling caps. Because remember, a decoupling capacitor is not ideal, so it does have inductance. And the way you mount it and the orientation of it is going to add more loop inductance. So sometimes you can actually add a decoupling capacitor and make it totally ineffective by improperly mounting it or using the wrong values or putting it in the wrong place, that the inductance is so much higher than the impact of the capacitance will give you. And the last thing to talk about is really signal integrity. So in signal integrity, there's a couple of things that I think about. One of them is impedance control. So for example, if you have a 50 ohm line, you want it to be 50 ohms throughout the whole interface, plus or minus a percentage, whatever your manufacturing tolerance is. And also termination, so you should have proper termination. You don't necessarily need termination on all your lines, but some of your high-speed lines or your critical lines like a clock net should have termination, so you should really review your app notes and your vendor recommendations and do some simulation to determine if you need termination. And then the third thing is reducing crosstalk. So you don't want crosstalk to become a big influence on your PCB design and your stackup. And so you can keep your traces further away from each other to help reduce the crosstalk. That's the easiest way to do it. And then also another thing to consider is PCB material loss. So remember the PCB traces, the copper traces, that has a conductor loss, and your FR4 dielectric material that has a dielectric loss. And your loss increases with frequency, right? So if you're under a gigahertz roughly, you might not need to really worry about the loss of materials. But if you're way out there at 20 or 30 gigahertz, that material loss is going to have a big impact on your design. It's going to attenuate and it's going to add noise to your signal. So you really need to consider your material loss as you go up in frequency. And then finally, kind of a subset of the loss is dealing with via stubs. And again, this is really in the multi-gigahertz range, but you don't want to have a via stub from a transition. Say you're going from the top layer to a middle layer in your stack up, and you still got a couple layers left. You're going to have that stub of your plated through hole via there, and at the right frequencies that can cause a resonance and that can cause loss and noise. So you want to avoid that as well. Ways you can avoid that is by trying to route your signals so they transition through your whole stack up, or you can pay money and do things like back drilling, and there's some other techniques as well. But really it goes back to the previous one, whether you need to worry about your via stubs is how much loss you can account for, what your loss budget might be. So overall, those are a couple of things to think about when you're doing your PCB stackup in terms of, if I think what would be an ideal PCB stackup for signal integrity considerations. Thanks for joining me today for this coffee break video. I hope you enjoyed it. If you have any questions or feedback, or if you have a topic that you'd like me to discuss next time, send me an email at tim@signalbytestech.com, and be sure to join us online at signalbytestech.com. Sign up for our newsletter, be notified when we do another one of these videos. Now, I'm going to have another cup of coffee, and it's probably time for you to get back to work. I'll see you next time.